we're going to hit Tab, Geo, to create a geometry object, and I'm going to rename this Sim. This is where I'm going to do the simulations for all the different elements in the project. So we hop on in, throw down a file node, and then you can grab from the Geo. I will provide this glass object for you to use, or you can simply model using a tube or some other glass object you might have. Something that's important to note if you are not using this object, or if you're just curious about the scale of this object, because it looks quite small at first glance, you need to take into account that Houdini units are default in meters. So when it's saying like 0 here to 1 here, that's 1 meter. So if this glass were 1 unit tall, it would be 1 meter tall, which is not realistic for a champagne glass. And dimensions like that come into play when you're running simulations. It's best to try to match the physical size of an object as close as possible if you want to get realistic results. For example, the glass that I've provided is 22 centimeters tall, which is about the average height for a champagne flute. So once you have the glass in your scene, we're just going to throw down a transform and just tilt the glass a little bit so we can have a little bit more interesting simulation. So it's going to have just like a little bit of a tilt to it, maybe tilt it forward some. And then we're going to set up just a really quick kind of working camera, just so we have an idea of what is and isn't going to be rendered. So to do that, you can just hold Control and click on Camera up in the toolbar, and that will automatically make a camera locked to your current viewport, and it'll also pull you back up to object level. So let's hop back into our sim, and if you click the little lock camera icon here, it will make the camera lock to your current viewport, so that way when you're panning around, your camera position, rotation, etc. will match to what it is you're doing in the viewport. So something like this is probably good for now. The main reason that I'm setting this up now is because we are going to create an object to emit fluid from. And ideally you don't want that object to be in the viewport. You don't want to see just a random sphere in your scene that's just emitting fluid with no real purpose, since this isn't a larger scene with like a bottle or other context. So let's go ahead and make our emitter. So we're going to drop down a sphere. And then again, it's going to look huge compared to the glass, because at default a sphere in Houdini is 2 by 2 by 2, so it's 2 meters in each direction, which is not ideal for what we need to do. So we're going to scale this down quite considerably. We're going to scale it down to 0.01, so it's a lot smaller. And I'm going to split the panes using this little icon here. And then I'm going to change this to a perspective viewport. So this way I can still pan around while also seeing what it is the camera will see. And also, just so this camera isn't distracting, I'm going to go back up to the object context, and on the camera I'm going to turn off its display flag, so that way it's not visible in the viewport. Okay, so now we have a sphere that's nice and small, and I'm going to template the glass so that we know where it is in space while also moving the sphere around. So that's done by simply clicking the flag, the second to last flag for template. That way we can kind of just see like a ghosted wireframe of it so we know where it is. So following the sphere, we're going to put down another transform node. Boop. And for this, we're just going to drag it up to a position that makes sense for where we want our liquid to pour in from. And this is where having the second viewport comes in handy, so you can see like if it's actually lined up over top of the glass. And then I can see in here, we can still see it, so it needs to move up some more. And I'm going to start it off a little towards the back of the glass. Okay. And then once we have that, I'm going to add a little bit of animation to this just to kind of give more variance so that there's not just a steady, continuous, uniform flow. And I'm going to do that by adding keyframes to the translation and the scale. The way you add keyframes quickly, you can hold Alt and left click in the boxes you want to add keyframes to. And then I'm just going to scrub forward in my timeline, maybe to around frame 45. And I'm going to just drag it forward so that it's moved forward in space. hit Alt, left mouse, and then move the uniform scale down to 0. So now if you scroll through your timeline, you'll see that it's moving forward and scaling down. I actually want to offset these keyframes a little bit so that we have a few frames where it's at full scale and so that the motion isn't happening exactly at the same time. And there are a few ways to move around keyframes you've already set. I'm going to hold down Shift and left click on the uniform scale value. That's going to pop up the animation editor. And here you can see the keyframes that you've created. And we can see the first keyframe where we set the scale to 1 is on frame 1. I'm just going to scoot that forward so that it's on, let's say, frame 12. So now the first keyframe for the uniform scale of 1 is on 12. We close that. So now we can see that it's moving as it was before. It doesn't start scaling down until we reach that first frame on 12. And then just to add one more layer of motion to our source, I'm going to throw down another transform, and I'm just going to add a little bit of a wiggle animation to the sphere in the z-axis. I'm going to do this using a sine function. So up here in the z transformation, put sine, and then $F, so that's the frame that we are currently on, and this is going to return a value between -1 and 1, and again those are meters, so that is way too much distance for it to be moving. So we're going to scale it down by 0.007. And then you'll notice that it doesn't really look like it's moving, and that's because it's moving very slowly. So we're going to scale up the speed of the sine wave significantly by multiplying the frame. So we do times 30. Now if you scrub through, you can see it wiggles back and forth a little bit, just adds a little bit more variance that'll come into play as we increase the resolution of our simulation. Okay, so now we have our emitting object, and we have our glass. Now, normally what you might do is you would go ahead and select your object and hit Emit Particle Fluid up here in the Shelf Tools underneath the Particle Fluid tab. This is a personal preference, but for my workflow, I prefer to have the dot network in the same area as where I'm sourcing. So I'm just going to put down my own dot net here, and I'm just going to rename it Fluid Pour Sim. And what that does is, now if you look down at the bottom, you can see there's a little checkbox for Fluid Pour Sim. So what this means is Houdini knows that this dot network exists, and right now, since there's a checkbox next to it, anything you do up here with the shelf tools to add to a dot network, it'll automatically put them in here. Otherwise, it would have created one up at the object level where you would have a dot network up here, and it would be kind of disjointed, and for me that gets a little confusing when you have a lot of simulations. Okay, so now that we have this, the dot network created, we can go ahead and select our emitter, hit Emit Particle Fluid. We're using this object. We're going to hit Enter, and hit Enter again. And it automatically will create some nodes for us in the dot network. So let's see what it's made up here. So at default, it creates this render node just to make sure that you're not rendering your source objects, but we don't need that, so we can delete that. And in addition to that, it also creates 2 geometry nodes up on the object level. These are where it's importing our simulation and turning it into polygons to render, and we're going to do that on our own, so we can also delete these. The main reason that I've decided to use the shelf tool for this, instead of just creating my own source and creating my own dot network just node by node, is because there's some really useful connections that it makes automatically. And you can see them here in the flip source that it's created. So here you can see we have particle separation, jitter seed, oversampling, all of these different attributes that are, if you click on them, you can see that they are connected to different values in the dot network. And again, you can do this manually. You could set up your own flip source node and then go into the dot network and make sure everything's connected, but I just find this a little bit more efficient to go ahead and let it handle those connections. Alright, so now that we have our display flag on our flip source, we don't actually see anything in our viewport. And the reason for that is the scale. So at default, it's trying to figure out what it does its best to guess some of the values that might be relevant for your sim, but again, this is a pretty small scale simulation, so it's not quite small enough for our purposes. So I'm actually going to break this connection here. And I'm going to do that by holding down Control, Shift, and left clicking. So that breaks the connection it had. And then I'm going to bring the voxel size down quite a bit. Let's say to around 0.003. Let's say to around 0.003. So now we can kind of see something. It's still not quite our sphere, and the reason for that is that shell thickness is turned on. What that does is it basically is treating the emission object as kind of a hollow object so that it just has an outer shell. And we don't really need that. We need the whole object to kind of be a solid volume. So we're going to turn off shell thickness. And now we can see our whole sphere, it's processing all of it as the emission source. So now we can hop into our DOP network. Let's go back to the first frame. And we can't really see anything. So if you scrub through the timeline, it doesn't seem to have anything. And again, that comes to our scale. So we're going to go to the flip object in our DOP network. And we're going to turn the particle separation down, similar to the voxel size that we did above. So now you can see we can actually see our particles for our flip simulation. Right now, if you were to scrub through your timeline, you'd see that the particles don't seem to be moving, and the reason for that is we don't have any other forces acting in the scene, and we didn't create any sort of velocity on our emitter, so they don't really have any values to push them around. So we're just going to put in a gravity force, and stick it in down here by the output. So that just applies a uniform force that matches gravity in the real world. So now if you move through your timeline, you can see that the fluid is falling as you might expect. Okay, so now let's bring in our glass object. Let's go back up a level, and here we have our glass object. And what I'm going to do is put down a collision source. This will create relevant attributes needed for an object to be used as a collision object. I'm going to left click and drag while holding Alt on this null. And that just is a quick way to copy and paste nodes, and I like to do that just for quick things that you might want to copy like nulls. So I'm just going to rename this out surface glass. So now you can see we have the surface of our glass. So let's hop back in our sim, and we're going to add a static object. I'm going to rename it glass, and we're going to point it to our out surface glass. And we'll add it to this merge node. And right now this mutual relationship is fine for what we have, but best practice is to be aware of the inputs you're using on your merge. And I'm going to change it to left affects right, and I'm going to drag this down so that this left object, our static glass object, is affecting our right object, which is the fluid object. Okay, so now we can see that our glass object is in our DOP simulation. So let's scrub through our timeline and see what it looks like. So as you can see, it's clipping right through our glass. And the reason for that is pretty easy to figure out. So we go to our glass object. We're going to turn off display geometry, so now we don't see it in the scene. And we're going to go to collisions, RBD solver, volume, and then we're going to check collision guide. So what this is showing us is what Houdini is interpreting as the collision object. And obviously this is not the shape of our glass. So we're going to create a VDB to use as our collision object. So we go back up a level and back to the collision source. Now I'm going to Alt left click drag again to create another null. This one is out VDB glass. And if we display it, we don't see anything. And that's because of the scale. So we're going to go to collision source, over to the volume tab, and we have voxel size once again. And we're going to turn this way down to something like 0.0015. And now you can see that we do get something that looks like our glass, but there's like some weird artifacts. It seems to be struggling with the upper end of our glass. And the reason for that is that the glass is extremely thin. And that's not really great for simulations, especially fluid simulations. So what we're going to have to do is thicken up this glass some for simulation purposes. So we're going to go back here after our transform, and we're going to put down a poly extrude. Display that, and then we're going to click this little arrow here to select a group for geometry that we want to extrude. So select that, and then I'm going to hit this little eyeball here, and basically that means it'll only select things that you can see in the viewport. I'm doing that so that I don't accidentally select any of the interior faces, because having those extrude inwards would not be very helpful for our simulation. So let's go ahead and grab just some faces all along here. And I'm just holding shift to add to selection without deselecting the other things. And I don't like these two odd pieces, so I'm going to hold control to remove those from the selection. Just try to make it a little bit clean. Okay. And then once you have some of the selection done, you can hold down shift and press G to grow your selection. So that way we have it kind of expanding outward from our previous selection. Let's do one more. There we go. And then hit enter. So now those primitives are selected over here for our poly extrude. And we're not going to extrude them a whole bunch, just by a small amount. So let's do by 0.011. So now you can see we've added some thickness to our glass. It looks kind of silly, but this isn't the object we'll be rendering, so it's fine to just kind of extrude it for collision purposes. So let's go look at how our VDB looks now. So now you can see we don't have any of those weird artifacts. It's handling this a lot better. If you want to look at the difference between the two, you can go over here and bypass the poly extrude and see how much of a difference that made. Okay, so now we've created a VDB, and now we just need to plug it into our simulation. You can already see that the collision guide for our static object has changed because of the thickness we've added to the glass. This is still not the best looking collision object, so what we're going to do is we're going to change the way that it's creating a volume for collision. So we're going to change this to volume sample by size. And this is a division size that will need to match our voxel size. So if we go up a level, and we find our voxel size, we do right-click, copy parameter, go back into the sim, right-click, paste relative reference. This way, if we change the voxel size for whatever reason, it'll update in our static object. And then the last thing we have to do is we need to point it to our VDB. So we just click on the proxy volume, out VDB glass. And now you can see the VDB we made, and it's a lot cleaner looking, a lot higher resolution. So I'm going to turn off collision guide and turn display geometry back on. And then I'm going to go up here to the viewport display options, and I'm just going to switch this to wireframe. That way we can actually see inside of the glass. So now let's scrub through and see how this is looking. So now you can see that the fluid is going into the glass. It's not just clipping straight through it. It's building up in a way that you might expect. Now that we have a basic simulation set up and working, let's go ahead and take a closer look at some of the attributes that are involved with the flip simulation. Okay, so first I'm going to go ahead and go back to one pane real quick. So we just have the one camera view. Then I'm going to go over to our flip object here, and I'm going to go to our initial data tab and scroll down. And down here we want to add viscosity attribute and add divergence field. So this way we have the viscosity attribute and a divergence field active on our flip object so that we can alter those attributes between the foam and the fluid simulations. And then we'll go to our flip solver, and we'll go to particle motion, behavior, and we'll want to check on add ID attribute. And what this will do is it will create a custom integer ID value for each particle, for each point. So that way we can easily edit these points later on. So once you've cached out your sim, like maybe your sim takes a long time to cache out, but you want to change specific things, like these flyaway pieces that we see right now. Maybe we want to delete those. Well, we want to have an ID attribute. That way we can isolate them after the simulation and do different kinds of effects to them as needed. And in addition to the ID attribute, we also want to age particles. And I'm turning this on because I know that post-simulation, I'm going to want to isolate some of the particles who are brand new to the simulation, which is why I'm turning on age, so that I can say these particles that are less than a certain age or greater than a certain age, I want to affect them in some way. So this way it'll go ahead and calculate that, so it'll calculate how long it's been since they were created. And then we want to go over to the Separation tab, and we want to check on Apply Particle Separation. So basically this kind of enforces that particle separation that we set on our flip object. So here we have our particle separation value. And what can happen sometimes is over the course of a simulation, the particle separation can kind of lose its overall value. It can kind of start to cause your simulation to compress a little bit visually. And turning this on enforces that particle separation. So that way we don't lose any volume over time. And then lastly, for the particle motion tab, we're going to go over to the vorticity. And we're going to add the vorticity attribute. This will make it so that we can access the vorticity attribute post-simulation, and we're going to use that to affect some things at render time. And then on our solver, we're going to go over to the volume motion tab, and we're going to go over to viscosity, and we're going to check enable viscosity. So even though we went into our flip object and we added a viscosity attribute, that does not automatically make viscosity come into effect within our simulation. And viscosity is basically what it sounds like. It's how viscous a fluid is. So something like honey is highly viscous. You know, it kind of sticks together and moves a lot slower, whereas water is a lot less viscous. And basically, adding the attribute does not enable it in the simulation. You have to enable it in the solver itself. So here we've enabled viscosity. And we're also going to go over to density. We're going to check on density by attribute. And this basically will allow us to set a specific density for some of our particles. We're going to use that to differentiate between the foam and the fluid of our simulation. And then lastly, we're going to go over to divergence, and we're going to turn on divergence by attribute. Similar to density, we're going to affect this attribute and create more differentiation between the foam and the fluid. Now that we have everything checked on, we can start messing with values and setting up a differentiation between the foam and the fluid, as I've mentioned, and we'll start getting into that in the next video.